Thank you, Professor, for this kind introduction. I will try to show you some of the most fancy and interesting application that we have done since I started my PhD on laser-induced graphene. And as you can imagine, for all the application that Professor mentioned, this cannot be a one-man work. So this is a full team that is working on this application, starting from Professor Marrocco as our guidance, postdoc and PhD students, but also master thesis students, which I wish to thank because they put a lot of effort and energy in the work. Now, as we probably understood from this workshop, LIG has been mostly used for sensor and low frequency application. We have seen supercapacitors, sensors for soft actuators. Probably you recognize some of your work in this slide. And the same is not true for antennas, because if we look at the number of scientific publications that we can find on Scopus for laser-induced graphene and laser-induced graphene antennas, we have I move a lot, so okay. We have a huge difference since its discovery in 2014. Just let's say 40 papers have been published. But the reason can be summarized in this slide. When we move from sensor to antennas, we have to face two main challenges. The first one is that antennas are way larger than sensors. We're talking about centimeter size against millimeter size. And we have a lot of issues related to its fabrication, starting from, for example, from the bending of the precursor during the laser, which can affect the quality of the graphene that we can achieve. And the second point, as Professor Greco clearly showed us during his presentation, sensors rely on variation to reduce stimuli, whereas antennas require very low nominal sheet resistance in order to achieve high efficiency and so to radiate properly. Now, regarding the second point, we can play with the laser parameters, the scan speed, the power, and the beam defocusing so the distance of the laser beam of the focal point from the precursor to enhance the sheet resistance. At the best we achieved was 4 ohm square, which is among the lowest value that we saw today. But this value, and especially the morphological features related to this value of sheet resistance, lead to important consequences when talking about antennas. The first important point that you have to keep in mind when dealing with antennas is that the penetration depth of an impinging electromagnetic wave on the surface of LIG is way higher than the thickness of the material. This means that this wave, when passing through the material, is only minimally attenuated by the material itself because of the ohmic losses. And this means that we can model this material as a thin, so a bidimensional material only defined by the Leontovich condition, which relates the tangential and component of the electric and magnetic field by means of the sheet resistance of the material. To make a comparison, the sheet resistance of the copper, by considering the same condition, so a thickness way smaller than the penetration depth of the material, is 4 orders of magnitude lower than one of the LIG. This means that for the LIG we have a higher and higher attenuation. The second point is related to this quite common expression, the expression of the resistance of the conductor, which is related to the geometrical feature of the conductor. So since we have a higher ohmic losses, we also need to decrease somehow the resistance of our conductor. And the solution is to use wide and, if it is possible, short traces. Short traces and short devices can be achieved also in the context of antennas, by mendering the conductor. Mendering is a quite common technique to shrink the size of the device. But if we mender our conductor, we produce some differential mode currents, so some out-of-phase contribution, which only contribute to the power loss rather than to the radiation. So instead of radiating the power, we are dissipating in the meandred path. Finally, another important consequence is that another important aspect of LIG for antennas is that there is an optimal size for antennas. The directivity, and so the radiation efficiency and the ohmic losses of the conductor increase with the size until an optimal value. So we cannot increase so much the device because after some point, the ohmic losses will increase more than the increase in terms of antenna directivity. Here you can see an example. We consider a standard dipole antenna in which we varied both the length and the width of our antenna, and you can see this beautiful bell shape trend in which we have an optimum of the gain of the antenna, which is a parameter which gives us the amount of power which is collected or radiated by the antenna, around 0.6 lambda, and so the wavelength of our antenna. And we see that this value is quite common regardless of the values of sheet resistance. But why is important to design properly the antenna? Because, okay, maybe I swapped the slide, but didn't change on the presentation. Because if we compare the radiation efficiency in terms of a wide and long dipole, a thin and wide dipole, and a meandering dipole, we see a huge variation from 68% of radiation efficiency, which can be quantified in, let's say, less than 2 dB loss. That, for those that are not familiar with this kind of units, represent a 15% reduction of the read range of our antenna, down to 2%. So 98% of power is dissipated and only 2% of power is radiated when we use thin meandred structure. So going back to the previous slide, we can answer to the, let's say, key question: how far are we from copper and standard conductors? The answer is that if we design properly our antenna and we optimize the laser parameter, we lose only 30%, which is not that much considering the benefit of using LIG as a conductor. But this was just one part of the story, because when you design an antenna, okay, you have to optimize the radiation efficiency, but you need also to guarantee that the power which is collected by the antenna or which is delivered from the source to the antenna is not dissipated in the middle. So you have to adapt the source or the load to the antenna impedance. And as we can imagine, LIG antennas are resistive antennas and capacitive because of the dissipation. Whereas IC, especially RFID1, are characterized by low input resistance and require an inductive impedance for the antenna in order to achieve conjugate impedance matching. So we have a discrepancy between the source and the antenna, which should be addressed by means of an antenna adapter, which is a block that here I schematized with this square. Clearly, adding a block in the middle between the source and the antenna produces some effect of the antenna. So in order to quantify the impact of this antenna adapter, we consider two metrics: the power transfer coefficient. Here we see the expression. I will not go too much in depth on this formula. Give us the amount of power which is delivered from the source to the antenna and should be as close as possible to 1. So all the power is delivered to the antenna. The effective insertion loss instead quantifies the amount of radiation efficiency which is lost because of the addition of the antenna adapter. And since it is a loss term, should be as low as possible. Here there are the typical class of impedance adapter that we can consider. We have distributed antenna adapters in which the inductive contribution that I was mentioning before is given by this circular path of the currents. and the lamped solution, in which rather than introducing circular path, which, as I remember you, introduce differential mode current, so power dissipation, exploit reactive components like inductor and capacitor to achieve conjugate impedance matching. What I want to put the emphasis on is that for the distributed, we have, let's say, a subcategory, which is the loop match solution, in which we don't have anomic contact between the LIG radiator and, let's say, the exciter of our antenna, which can be made both of LIG or, let's say, metallic conductor. This is a small price that we have to pay in order to achieve conjugate matching. Here there are the results. As you can see, the distributed adapters are quite not adequate for this purpose. If we look at the loss term, so the insertion loss, we lose 17 dB, almost 20 dB because of that component. In the case of the copper LIG loop match solution, the situation is quite better because we lose overall 6 dB, and losing 6 dB is like reducing the reading distance of our antenna by a factor 2. So we are not losing that much compared to metal. But if we look at the lamped solution, so if we consider one or multiple reactive component, we are able to minimize this loss down to 0 dB. So we can use a single inductor to tune the impedance of our antenna to the impedance of our load without paying any price, so at any cost. We also validated our numerical results by means of some prototypes that well compares in terms with respect to simulation. Here there is the gain of our antenna, both simulated and measured, and we see a good agreement regardless of the antenna adapter that we considered. But after the fundamental parts, now I want to show you some application that we developed based on this knowledge. You will see the faces of these master students that worked on this project. And the first solution that I want to discuss on is related to smart packaging. The reason behind the use of LIG for smart packaging is quite simple. We will not spend so many words on it, but what I want to describe is the rationale behind our device. So we have a wireless device which comprises a sensor, in our case an interdigitated capacitive sensor, and an antenna. These two are connected by means of an RFID IC, which is responsible for both the communication with an external RFID reader and for the extraction of the capacitance. Why the extraction of the capacitance? Because the sensor is loaded with a chemical interactive material. In our case, is polyethylene glycol diacrylate, PEGDA, which swells upon exposure to triethylamine or to amine in general. Amine is a product of food spoilage, so we intended to use this solution to monitor the food spoilage. Why I called this structure heterostructure? Because we use different laser settings within the same manufacturing process to engrave the sensor and the antenna. And here there is the result. This is our tapered dipole antenna with the interdigitated capacitor in between the two arms of the dipole, and you can see the different laser settings here for the interdigitated capacitor and for the antenna with different values of sheet resistance. For the sensor, we choose these settings because we wanted to optimize the resolution during the engraving to create this small gap between the fingers of the capacitor. Here there is the test of our sensor. You see that in terms of electromagnetic response, once again there is a good agreement between measurement and simulation. And if we look instead to the variation of capacitance, which was collected wirelessly by our sensor, you can see here the setup with this fish hanging outside the window for, let's say, safety purpose. We have a short variation of capacitance upon the exposure to different concentration of 3-ethylamine. And by means of simple machine learning algorithm, we were able to establish the concentration of 3-ethylamine which the sensor was exposed to. Another application, smart prosthesis. Why smart prosthesis? Talking, let's say, in general terms, once we have to deal with a surgery for the implantation of a medical device, we want to exploit this device as a gateway for the inside of our body. So we want to exploit the prosthesis itself to collect data, both logistic, let's say, identification data and sensing data. But how LIG can be considered a promising solution in this context? The reason is explained in this picture, because PIC, which probably all of you know, which is precursor of LIG, is steadily replacing metal and ceramics into prosthesis. Why? Because it is lighter, it is compatible with imaging techniques, and compared to ceramic, it is less brittle. So there is less risk of fracture and so infection for the patient. And here there is our vision. We envision the LIG as a tattoo on a PIC prosthesis that we can leverage to extract data about the health status of our patient. We tested our prototype in a liquid phantom mimicking the muscle tissue. And here you can see the gain of our antenna, this again tapered dipole antenna. What I put the emphasis on is that once again it is straight and it is wide to minimize the ohmic losses. And the interesting part is that we have 20 dB margin, which is a lot with respect to the minimum required transducer power gain to establish the telemetry link from outside of the body at 3.5 centimeter distance. This means that we can reach distances up to 9 centimeters from outside of the body. Another application, I will not go so much in detail because on Tuesday we'll give you a talk on this topic, so you can find more details on that presentation. But here the idea is to use the LIG as a mask to selectively deposit a metallic anion on the surface of a dielectric object. So we create the pattern with the laser, and then we exploit the redox reaction behind the electroplating process to selectively deposit metallic anions. Here there are two beautiful SEM images of the LIG before and after the electroplating process. You see how the metallic anions deposit following the same morphology of the LIG trace. And here you can see the energy dispersive X-ray spectroscopy, difficult name to pronounce, in which you see the ions copper in blue and the LIG residual in yellow, which are in the groove of the LIG trace. So we can still preserve the morphology of the LIG even if we are coating with the metallic anions. However, when we talk about coating, we have to deal with the homogeneity of our coating. And it is particularly important for antennas because this homogeneity means the current path is altered somehow. So we induce frequency shift, impedance mismatch, and loss of efficiency. So in order to optimize the coating, we need to understand what are the physical laws that govern the deposition phenomena. And these are the Faraday law, which relates the amount of mass of metal deposited on the surface to the surface current density during the process. And the surface current density we can see which is related to the conductivity of the cathode, so to the sheet resistance of our cathode, and so to the laser parameters, and the voltage gradient, which is instead related to the geometry of our structure. Clearly, we can optimize it by a trial and error procedure in an experimental way, but it is time consuming and is not so efficient. So our idea is to optimize by design the homogeneity of our deposition by choosing an optimal number and position of bias point on the surface of on the edge of our cathode to optimize the homogeneity of the surface current density and so of the deposit itself. Here you can see an example in which we use a gamma match implanted dipole antenna with different position. We consider an index that I will show you in my talk on Tuesday, and you can see how beautiful and compact can be the coating on the surface of our antenna. Transient devices, another, let's say, keystone, another promising application that we have in mind. It's not necessary to spend so many words on the importance of transient implantable medical device. If the device is not biodegradable and it is transient, we need an extraction surgery. And this event can be painful for the patient, so we want to avoid as much as possible. Even if the device must not removed, we may have the need of temporary devices like pills and scaffold. So there is an important need of transient medical devices in the industry. Clearly, when we talk about transient electronics, we have to deal with the transient biodegradable, let's say, dielectrics and biodegradable conductors. We have a lot of choices, plenty of choices for the printed dielectrics, but the same is not true for conductors, because even if there are some solutions, these are quite difficult to handle and to manufacture. So our idea is to combine laser-induced graphene and these biodegradable dielectrics, in particular the polyvinyl alcohol, to create transient antennas. And here there is the process. As some of you showed before, we use a quite straightforward transfer technique. So we solubilized the surface of the PVA in order to make it infiltrate inside the LIG flakes. We place our antenna on top and we apply for a limited amount of time variable pressure and heat. So after 20 minutes, we peel off the LIG, the captain from this assembly, and we were able to achieve a complete transfer. Complete transfer, which is quite efficient because we are able to transfer even very small detail, as small as 300 micron, like the pad of this small RFID IC, and that were connected by means of conductive epoxy. And even if there are some small surface defects, this is not detrimental for the performance of the antenna, because we tested 2 prototypes in the early stage of this project, and we achieved a good agreement between measurement and simulation with a variation of just 1 dB/2, which is completely understandable in this in the manufacturing process. And here you can see an example of transient antenna, because in just 1 hour, the conductor first and then the PVA completely degrade in water. Another application, I almost finished, I promised. Also in this case, Professor Marrocco will give you a nice lecture, so take note of this schedule. And in this context, we are talking about a different scenario. We're talking about security. Why security? Because as you all know, even if we use the same settings, the same precursor, and the same laser machine, we cannot achieve in the smallest scale the same LIG trace. So the idea is to leverage this imperfection related to the fabrication process to create physical unclonable function. For those of you that are not familiar with the physical unclonable function, we have an external stimulus, which is the challenge, upon which the device, which instead is this antenna, responds with a unique response. In our case, the challenge, so the stimulus is an RFID interrogation, the response is the scattered signal of the RFID antenna. To go more in detail, this is the reader which emits a signal to the RFID IC. This power emitted by the reader is collected to empower the circuitry inside the RFID IC, and this power is employed by the IC to switch rapidly between two states of the impedance of the IC, and so to reply with a digital code. Well, this signal is collected by the RFID reader, and for each frequency at which this operation occurs, and for each power, we are able to collect this voltage here, which is the scattered signal, with some mathematical processing can be related to, make adimensional, and by considering the module of this signal for each frequency and for each power, we are able to create a fingerprint related to that device. Clearly, to move from an analog to a digital signal, we need to apply some processing. So this is our fingerprint at each frequency and for just one power. This signal has been detrended, so the average value has been removed, and it has been equalized. Finally, it has been binarized in order to have a digital code. Here you can see the response of 30, let's say, identical devices at different powers. And even if these devices are in theory identical, you see how different is the response of each of these devices. So for each device, we can create a unique key. Here you can see a snapshot of the physical unclonable function of the device that can be considered as a key related to that device. Clearly, in order to be a key and to be secure, we need some metrics to consider as it is. And the metrics that we consider are the randomness, so how random is the key that we are generating, and how unique is this key. We can use some expression like the Shannon entropy and the Hamming distance, but what I put the emphasis on is that the degree of freedom, so the variables that we can achieve with this kind of key is 116 bits, which is very close to 128 bits of standard cryptography algorithm. Last but not least, LIG can be used also in smart environments. Probably some of you know about frequency selective surface absorbers, so solution applied over buildings to shield the content or the people living inside the building from the external RF environment. Here I use ChatGPT to envision this kind of structure, and you can see how big, without any further information, the AI model considered this skin, and is not so far from the reality. In the reality, this skin, in order to be effective, needs to be large. But if these are made by metal, you can imagine how difficult it can be to fabricate this kind of structure. They can weigh a lot, they cost a lot. So our idea is to use the LIG to fabricate this kind of skins. In this case, we use consider small prototypes for the sake of fabrication, but it can be extended because the process is sustainable, as we learned from this workshop. We have no weight increase because it's the same weight of polyimide, which would be present also in the metallic structure, and it can be engraved over conformal geometries. Clearly, because we have ohmic losses, we have gap of performance with respect to metal, but we were able to optimize the performance of our device by resorting to a multi-layer structure to achieve the same selectivity of metallic structure. You see that this is the response. Where there is the peak, the structure attenuates the most, and the sharper the peak, the narrower the bandwidth of our device, so the more selective the structure. With just 3 layers, which is 1.5 millimeters, so not that much thick, we were able to achieve a very sharp notch. So, to conclude my talk, LIG can be used to enable the fabrication of sustainable wireless systems and devices, even if the efficiency, the gap in efficiency poses some limits. However, if we talk about RF devices around UHF and so around 1 gigahertz and beyond, we are able to achieve adequate performance. Remember the 30% gap of performance with respect to metal. We can functionalize the LIG with other materials for intelligent sensing, hybrid fabrication, electroplating, dissolution, and any other kind of application that you showed us during your talk. What are the applications in which we envision the LIG the most? For sure, embedding smart sensor, let's say, on prosthesis as a tattoo. Also for security-based application, remember the degree of freedom that we achieved with the physical unclonable function with this technique. Smart packaging. We can, some of you inspired us in using more sustainable materials for this kind of application, and for sure I will go more in depth in this kind of application, but also transient and disposable biosensing devices, for example, for wound monitoring. The job is not done, obviously. There are still some open points. For example, the integration of discrete components. The conductive epoxy that we used so far introduced further losses to the losses of the LIG. In terms of losses, we want to achieve higher conductivity to minimize the losses further, and we want to functionalize the precursors to enable some specific function during the engraving, but also gigahertz band application like the FSS, reconfigurable intelligent surfaces, and absorb. So I concluded my talk, and if you want to learn about our research topic, our work, here you can see some interesting tutorials that we published in 2024, so they're quite recent. This one is more related to the application. This one instead is more related to the technical aspect of our work. So if you have any question, I am happy to answer to it.